Okay, welcome back. In this video, we are going to continue our talk through chapter 12 and talking about reactions. And we are going to work to try to understand things that are called reaction surfaces or potential energy diagrams. Just a warning, this may be my favorite way of depicting chemical reactions. And so I might get excited. Okay, so a lot changes during a reaction. We were talking about this in the last video. The bond lengths, the bond angles, the types of bonds, the chemicals themselves. And so it really gets difficult to concisely communicate everything that changes. So to do this, we start to use a tool known as potential energy diagrams. And this is a picture and an attempt at trying to communicate what is happening in a reaction. Now, when reactions get complicated, these potential energy diagrams must be simplified, and we must keep our focus on one point. And trying to figure out what point and what is the correct way to depict the potential energy surface is a very active area of research. In fact, I would say that most physical chemists at some point study a potential energy diagram in some way or another in their research. Okay, so let's start with a basic reaction. In this reaction, we have HCl being reacted with, we're going to put light, H nu. We're going to shine light on HCl, and we are going to break the bond between the hydrogen and the chlorine, creating two neutral atoms, the hydrogen and the chloride. Not even the chloride, the chlorine atom. And what we are going to do is on the y-axis, we are going to put on potential energy. And on the x-axis, this is the bond length. Or more precisely, this is the distance between the hydrogen and the chlorine. And so when we have HCl sitting around at room temperature, it has an optimum bond length. That optimum bond length of HCl, that equilibrium bond length, that has the lowest potential energy. This is the definition of the bond. Now, as we start stretching that bond, and so we start moving the hydrogen and the chlorine further apart, the energy is going to rise because the reason that this bond is at the minimum energy is because we are exactly balancing the attractive and repulsive forces between the nuclei and the electrons. Those are the attractive forces. And the repulsive forces between the two nuclei and between electrons. And as we start pulling these atoms apart, the electrons of the chlorine are no longer being able to see the protons of the hydrogen. And so this is the attractive force. And so as we get these further and further apart, the attractive force is lessened, and therefore the repulsive force between the electrons of the hydrogen and the electrons of the chlorine, this is the repulsive force, that becomes more prominent. And so the energy starts going up as we increase that distance. But eventually we will break that bond and we will get free atoms, hydrogen and chlorine. And at this point, the potential energy is defined to be 0 because they are now behaving as individual atoms that do not see each other. And so there is no attractive or repulsive forces between these atoms. This diagram, this mapping of how the potential energy is related to the distance between the atoms, this is a potential energy diagram. Now, in this case, we only have one bond involved. And so, therefore, we really only have one dimension for our potential energy diagram. So now let's think about what happens if we have more than one bond. So the number of dimensions of a reaction surface is the same as the number of vibrational degrees of freedom. So that is 3n minus 6, where n becomes the total number of atoms of all reactants. And so if we think about this reaction where we have the fluoride atom reacting with hydrogen gas to produce hydrofluoric acid and a hydrogen atom, our number of dimensions is going to be equal to 3, that was a bad 3, times 3 atoms minus 6, which will be 3 dimensions. And what we did was, in this, we used the vibrational frequency. And so the vibrational frequency, nu, is related to the bond length. It's going to be proportional to this bond length. And it's an energy. And so what we can do is, on one axis, we are going to map the distance between the hydrogen atoms in the H2. And then on another axis, we will map the HF bond angle or bond distance, and we will ask what is the energy of this bond. So if the energy is, so when that, and I'm going to erase this because this is, we're gonna further explain this. So when we have things very far apart, so this is saying that this corner up here is where we basically have an H, an F, and an H, all infinitely separated. And so this is basically our sort of zero energy. That's that point. And what happens is that when we have H2 formed, we have a lower energy state. These graphs, these are the same, they're just rotated. And we have another low energy well whenever we have the HF bond formed. And there's a path between these. that stays out of these sort of super high energy areas. These high energy areas are where that either those bonds are completely broken or that there's high repulsive forces or bringing those atoms way too close together. And so there's a valley between these hills, and that is the pathway of the reaction. So normally we don't really show these diagrams as these 3 dimensions because they get really hard to read. And so what we do is we try to explain this based upon more of a 2-dimensional picture. And so to understand this 2-dimensional picture, we are going to need to talk about some vocab. The reaction coordinate is really talking about what we are going to measure. And so I can map this potential energy diagram just in terms of the HH bond distance. And so I would have the potential energy versus the HH bond, and I can get a 1-dimensional picture where we start at some energy and we go to another energy. And what we would end up seeing is something that looks like this, where this is where we start with a good HH bond, and then down here we no longer have an HH bond because we have products, and the F is just hanging out over here. Now, along this reaction coordinate, there is a highest energy state. This is known as the transition state. And oftentimes, that transition state is this condition where we kind of have half bonds between our reactants and our products. And then the last piece is the activation energy. And the activation energy is really talking about how much energy is it going to take to get over top of this hump. And so in order to reach the transition state, some energy is always going to need to be added. And how much energy has to be added is the activation energy. This difference between the reactants and the products, this potential energy difference, this is going to be related to our thermodynamic properties. And this is going to tell us how much energy has to go in or will come out from that chemical reaction. And that is what we are ultimately going to be working with as we try to understand things like entropy, enthalpy, Gibbs free energy, etc., in terms of chemical reactions. Okay, so let's summarize. Chemical reactions are processes that change the chemical bonds in the system. The difference in potential energy between 2 separated atoms and 2 atoms in the chemical bond is typically around 400 kilojoules per mole. This is 160 times greater than the thermal energy at room temperature. Chemical reactions often occur with energy changes much greater than the energy already available from the random motion of molecules. And so this means that in a process of doing a reaction, we can get energy from the system. And the reaction surfaces and the potential energy associated with the chemical bonds, showing the reaction surface graphs the potential energy associated with the chemical bonds, showing how much energy can be released or absorbed from any given pathway. And so I'm going to go back a little. Okay, I hope that was helpful. This is the first part of chapter 12.2. And you can now do homework problems 1 and 2.